Hi folks, welcome back to Physics with Captain Rod. Making this video here to help you out with numbers 2, 3, and 4 in your physics homework over thermodynamics. So number 2, it says, let's see, a lead vat is 12 meters long at room temperature, 20 degrees centigrade. How much longer is it when it contains boiling water at 1 atmosphere pressure? All right, so it's some sort of container that they're talking about, and it's made of lead. And it has a certain length that was given in the problem. In my example, it's 12 meters at a temperature of 20 degrees C. Now, then what happens is somebody fills it with water that's boiling. So this is now boiling hot water, and water boils at a temperature of 100 degrees C. Now, lead being a metal, it conducts heat, so lead will very easily take some of the energy from the water, and its temperature will go up, and heat will continue to transfer from the water to the lead until the temperature of the lead, the final temperature of that lead, is 100 degrees C. So what's going to happen is we're going to have some thermodynamic expansion. This thing is going to get larger, basically. Now, I'm going to greatly exaggerate it, but we're going to have this change in length here. Now, you couldn't tell by eyeball that the length got larger, but you know, because length changes, these are very, very, very small numbers, fraction of a hundredth of a percent or so. But there will be a small measurable change in length. And the change in length is a linear function. Length changes very linearly with the original length and the temperature change. And then the constant's called the coefficient of linear expansion. So you're going to want to look this up for lead. And again, that's called the coefficient of linear expansion. It will have units of 1 over degrees C or 1 over Kelvin, either one. The original length is given in the problem. The temperature change you can get from these numbers. It's important to realize this is a delta T. So like if you had an initial temperature of 20 and a final temperature of 100, then the delta T would be 80 degrees C. And that will allow you to calculate the change in length for the lead. Let's talk about number 3. Number 3 is pretty darn similar. Actually, it's virtually identical. There's an aluminum wing on a passenger jet. So I'm just going to draw a quick sketch of the wing. Presumably it looks something like this. And that length is given in the problem. In my example, it says 26 meters at 27 degrees centigrade. At what temperature would the wing be 7 centimeters shorter? So if it's 7 centimeters shorter, then the change in length would be minus 0.07 meters. 7 centimeters would be 0.07 meters, and it's shorter, that's why the minus sign. Then we've got that our change in length is equal to our coefficient of expansion times the original length times the temperature change. So use this value here. You're going to look up the coefficient of linear expansion for aluminum. This number right here is the 26 meters. Yours might be different in the problem. And then you're going to be able to calculate a temperature change. Now this is going to be some negative number, and it's going to be small. It might be something like, actually it might not be that small actually. It might be something like minus 20 or something, I don't know. If this comes out to be minus 20, to answer the question it says, at what temperature would the wing be 7 centimeters shorter? Well, you take your original temperature and then subtract off whatever this is, and that'll get you the new temperature. So that should be enough on number 3. So 2 and 3 done. Whoops, 4 not done. Let's chat about 4. All right, so number 4, it says an air balloon does 55 joules of work while absorbing 79 joules of heat. What's its change in internal energy? So this is a question about the first law of thermodynamics. First law of thermodynamics says this: the change in internal energy of some sort of system is equal to heat added plus work done. Or like in equation form, this is usually represented with a Q and this is represented with a W. Now all you have to be careful of when you calculate these things is you have to know the plus or minus signs. The heat term is considered positive when it's into the system, making the internal energy go up. The heat term is considered negative when it's out of the system, which would make the energy go down. The work term is considered positive when the system is compressed. So whenever your volume is going down, this will be considered positive. When you compress a gas, that has the result of making its temperature go up and hence increasing its internal energy. And then if your volume goes up, this term is considered negative. So the work is positive when the volume goes down, negative when the volume goes up. So in number 4, it says air in a balloon does 55 joules of work while absorbing 79 joules of heat. So there's some sort of balloon, and it says the air in the balloon does 55 joules of work. So I would interpret that as, since the air it says is doing the work, the balloon must be getting bigger. Therefore, the work term will be negative. Then it says while absorbing 79 joules of heat. So this is going to be positive, some number, whatever your number is in your work. And then the work term is going to be negative, and that's going to give you the change in internal energy. So that should be enough on that one. I'm going to just call that a day right there and make a different video on a different set of homework. Right? Hope that helps you get these done. Have a great day.